So what's the difference between two spaces being homeomorphic and homotopy equivalent? First, let me say what I mean by a space. A set of points with the notion of closeness. In practice, this means defining certain subsets of the space to be open sets, and the collection of all open sets be closed under finite intersections and arbitrary unions. So, a homeomorphism between spaces x and y is a function from x to y with certain properties. F is 1 to 1, which means that if a point in y is mapped to by some point in x, no other point in x also maps to the same y. Also, F fills y, which means that any point in y has some point in x that maps to it. This is called being onto. If a function is 1 to 1 and onto, we call it a bijection. All right, so F is a bijection in a homeomorphism. There's two other properties. F is continuous. Now, in the language of open sets, that means the preimage of an open set in Y is an open set in X. Okay? So this is dependent on the topology on X and Y. Also, the inverse, going back from X, so from Y to X, is continuous. Means any open set in Y that you care to pick, the preimage of that under any open set in X that you care to pick, the preimage of that under F inverse is also an open set in Y. So let's see some examples. F going from circle to a square. Since this depends on the topology, let me tell you about the topology on these. The set of open sets. Embed the circle in the Cartesian plane. Open sets in the Cartesian plane are balls. So any intersection of the circle with an open ball in the plane is an open set, and likewise for the square embedded in the plane. And here I'm just saying where these points get mapped. All right. So this piece of the circle gets mapped to this piece of the square, this piece of the square from this piece of the circle, and so on. And that is a homeomorphism. Open sets match up. F is continuous. It's 1 to 1. It's onto. This is a homeomorphism. So a circle is homeomorphic to a square. Here's a non-example. Let's take the circle again. The same topology. And map it to this half-open interval from 0 to tau. Now, we have an open set here. From here to there is an open set in the induced topology on this open interval. The preimage of that is the set from here to here, which is not an open set in the induced topology on this circle. So this F is not a homeomorphism. Okay. Another non-example. Take closed interval 0 to 1 with the usual topology and a square segment to the plane with, again, the usual topology, and try to make a map taking one onto the other. Well, you may have heard of space-filling curves. We can take this line segment into this plane segment like that in a first iteration, and then in a second iteration like this. Oops, this should go in further. Like that. And then in a third iteration, turn all these humps into copies of the puzzle piece type thing here, and so on and so forth. All right. In the limit, this will be a space-filling curve. Every point in this solid square will be mapped to by some point in the line segment. I said this is a non-example though. Where does it break down? Even though this line segment never intersects itself in any of the iterations, in the limit, it's like a line that approaches a curve and in the limit shares a point with the curve. This line will be infinitely self-intersecting and so violates the one-to-one condition for a homeomorphism. So this line segment is not homeomorphic to this solid square. Okay, so now let's talk about homotopy. A homotopy is a continuous deformation of maps. From X to Y to another map. We can write this as a single function from the first space cross an interval that will define the endpoints of our deformation onto the second space Y, and require that H be continuous in both variables, and that H agrees with F at one endpoint of this interval and agrees with G, F of X, G of X, at the other endpoint of that interval. And let me show you an example of this. Here's a function from the real line to the real line. F takes any point x, any number x in this case, to the square. G, also function from the reals to the reals. G takes a number to its sign. Two maps from the reals onto the reals, and a homotopy between them. You can write this out explicitly. All right. We can see that when t is 0, h matches up with f. When t is 1, h matches up with g. And we can see that h is continuous in both variables. So h is a homotopy from the map f to the map g. So what does it mean for two spaces to be homotopy equivalent? Let's picture X as just any old space here, and Y as just any old space here. F, a map from X to Y, and let's say G is a map from Y to X. The only condition I'm going to put on F and G is that they both be continuous functions. Let me show you a special function on any topological space, let's call it M. The map that takes a point back to itself is called the identity on the space. So this is the identity on M. Every point in M is being taken right back to itself. Now, let's follow a point around. Let's take a point of X, let's call it little x. Let's operate on that with our operation taking X to Y, that's F. X is taken to the point F of X. And now let's operate on that point in Y, F of X, with our operation taking Y to X, points of Y into points of X. So this is G of F of X. Okay. So, just looking at space X, the composite map looks like a loop where the starting point and the end point are not the same, not necessarily the same. From X to G of F of X. And now we have the basis for our definition of homotopy equivalence. If there exists continuous F from X to Y, G from Y to X, such that G of F of X is homotopic to the identity on X, and F of G is likewise homotopic to the identity on Y, X, and Y. Our homotopy equivalent. So this is a different sort of equivalence than our being homeomorphic to each other. Homotopy equivalent is different. And let me show you a couple of examples. For instance, suppose X is our space there, and Y is just a single point. All right, F takes every point in X and puts it onto the single point in Y. So that's our map F. There's also must be a map G from y to x, and there it is, that's G. So now let's take a look at the maps on X. Here's the identity map. Everything gets mapped to itself, little loops on every point. And this is the map from X to X, G of F. Well, F takes this middle point to the point Y and then back to the middle point. So there is a loop here. But F takes the endpoint to the single point Y, which goes to the single point here. So there. Likewise, there. Likewise, every point in X gets taken to that single point, which is the image of Y in X. And let's look at how the deformation might work. Let's move the endpoints of these loops. Well, this loop is the same, it doesn't change, it stays there. Alright, this endpoint of this loop needs to move all the way here, so let's move it halfway. Just see it in progress. And the endpoint of this little loop here needs to move all the way here, so let's move it halfway, and so on. Like that. So by moving these endpoints of the loops, we get a continuous deformation from the identity map to the map G of F of X. The map F of G of X is very easy on Y. This is the identity map, and taking G takes the single point of Y to this midpoint of X, and F takes the midpoint of X back to the single point of Y. There. They're exactly the same. There's the identity, and here's F of G. Okay, so a line segment is homotopy equivalent to a single point. That doesn't happen in homeomorphism. There's no homeomorphism from a line segment to a single point, because this F would not be 1-to-1, this G would not be on 2. So there are different things. All right, another example, or one more example and one more non-example. A very similar example to the one before is a solid square being homotopy equivalent to a line segment. Squish it down and then embed. All right, and you can do that. Here's a non-example. Two things that are not homotopy equivalent, so you get a flavor for homotopy equivalence, what it is and what it isn't. Let's take X to be a circle in the plane and Y to be a single point. Now, F obviously takes every point in X to the single point in Y. G will take the single point Y to some point, call it this, in X. Let's look at the identity map on X. So loop here, loop here. There's a loop everywhere. Just takes points of X to themselves. And now let's take a look at G of F. This loop stays the same. These points are all taken to one point. Now, can these two maps be continuously transformed one into the other by, say, moving endpoints around? Well, let's think about moving the movable endpoint of these loops. Where do they need to be moved? They all need to be moved here. This one's easy, just shift it around. This one's easy, shift it around. This one's easy, but notice. This one here, directly across, say. Does the movable endpoint go to the right or to the left? Well, if it goes to the right, to be a continuous map, to be a continuous deformation, the ones next to it need to also go to the right. And the ones next to that need to go to the right. And the ones next to that. So there's going to be some point in here where to make a deformation between these, you must tear it apart. Something going to the right of the split going to the right, to the left of the split, and points moving to the left. All right, and that's not continuous when those things are split apart like that. So okay, so we have homotopy equivalence dealing with continuous deformations of maps, and homeomorphism being continuous bijective functions with the continuous inverse. So that's the difference between a homeomorphism and two spaces being homotopy equivalent.